Hello, everyone. My name is Elisa Baum, and I run demand generation at Imply, and I welcome you to today's webinar. Before we begin, I just want to do a little bit of housekeeping. So the first thing is, during the presentation today, you will be on mute, but if you have any questions at all for the presenter, please go ahead and put them into the Q&A section of the Zoom webinar panel, which you'll see on the bottom of the screen. If you put your questions into chat, we probably won't see them. So again, please put your questions in the Q&A panel. At the end of the presentation, we'll take as many questions as we have time left. And those that are not addressed, I'll send them to the speaker, who's Gian Merlino. And hopefully we can get your questions answered that way. So today's presentation is what's new in Imply 3.3 and Apache Druid 18. It's being presented by Gian Merlino. He's Imply's co-founder and chief technology officer, and he's also one of the main contributors of Apache Druid. So with that said, I will go ahead and turn the floor over to Gian, and I hope that everyone enjoys the presentation today. Go ahead, Gian.
Thank you. Hey everybody, thanks for the intro, and thank you for joining. Like Lisa mentioned, this presentation is about what's new in Apache Druid 18 and the Imply release based on that 3.3. I'll just be covering the Druid pieces of that today. There's of course a few other interesting things that were in Imply 3.3 outside of Druid on the pivot and the clarity side, so check out our site for more info on that. Okay, that being said, who am I? I'm Gian Merlino. I'm a committer and PMC chair on Apache Druid, the data project that we all know and love. Co-founder and CTO at Imply. We're hiring, of course, so feel free to talk to us if you're interested in that kind of thing. And without further ado, I want to start talking about a couple of highlights in the most recent release that we did a few weeks ago. So I want to talk about two highlights. There's a lot of things that we did, but I'm going to talk about two of them in this presentation. The two I want to talk about are SQL joins and query lanes. SQL joins are, I think, what a lot of you are here for. It's our big headline new feature. But I'm going to talk about query lanes as well, because it's a feature that I find very exciting and interesting. And I think a feature that a lot of people know they need, and a lot of people need even though they don't realize it yet. So we'll mostly talk about joins, and then we have a few minutes at the end talking about what query lanes are all about. This little teaser picture of a carpool lane. You can think about that as we get to that section. First off, joins. What's going on with that? Okay, so the first thing is what's the motivation for joins? It may be obvious, but I'll talk about it anyway. So other than the fact that it's a common database feature, why do databases want to do this? Why do we want to do this? What caused us to want to implement this in this version? So by way of motivation, imagine a retail sales data set. The department for a product may change from time to time. So let's say that you have a spray bottle, and the spray bottle is considered gardening supply up until March 3rd, when it begins to be considered a cleaning product. And let's say that query time, you want to know the latest department. So you don't actually, you want that to even apply to historical data. Next slide. Oh, sorry, my slides are a little bit wonky. We'll get through it together. Okay, so without joins, all older records must be re-ingested for the department to stay up to date. You cross out this, you re-ingest older data that says a spray bottle is a gardening device, and you re-ingest as a cleaning product. And this is useful for a wide variety of things. Useful for defining product names based on SKUs, defining product categories, defining product departments, and even for things that are not products, as we'll see some other examples later. So without joins, the classic Druid mechanism was you would re-ingest all older records, and that would cause departments to stay up to date. Sorry, for some reason the presentation tool I'm using takes a little bit of time to go to the next slide. Motivation, okay. So with joins, this mapping is done at query time, which simplifies the data architecture. Instead of storing the department in the actual table, you have two tables. You have a product department mapping table and a sales table, and you can apply the product department mapping at query time. So that simplifies data architecture. It means you don't need to reload everything. It does incur a performance cost, as you might imagine, which we'll talk about later when we talk about how these queries actually get run. But the simplification of architecture and the ability to always use the latest metadata is really valuable for a lot of use cases. Other motivations for joins. Number one, BI tools generate join queries. We want Druid to be able to integrate well with common business intelligence tools applications. Number two, analysts, people that work with data are trained to use joins when writing SQL queries. We want Druid to support as much SQL as possible. Druid's really come a long way from the very early days. I forget which version we introduced SQL support. I think it was 9 or 10 or 11, somewhere in that era. Really come a long way from the early days. We didn't support SQL at all, to supporting SQL without joins and now SQL with joins. And they also come up surprisingly often. So I went through the example of the fact dimension join, and that's maybe the one that comes most readily to people's minds. But a lot of things are really joins in disguise. So when you want to filter on a subquery, that's actually a join in disguise. And a lot of other kinds of queries that you want to do, like if you want to filter on the top 10 items of something, that's the join in disguise. A lot of queries that you want to do actually turns out to be really joins under the hood. So this actually is a meaningfully large expansion of the kinds of queries that Druid's able to do. So let's look at another example. So here's a more complicated example. The example that on the first slide was just a simple example of a product to product department. This is a little more complicated example. Let's say we have this data set called flights, which is you can tell I put this example together before recent events began, back when flights were still relevant to a lot of people's lives. You have a data set called flights, which is describing flights that are happening. And then you have tables that describe information about planes, information about the weather, information about airports, and these can be modeled as join tables. And so with this somewhat more complicated example, let's look at a few queries we can do with this. And the reason I want to look at a few queries is where I want to give you a flavor of how Druid will actually execute these under the hood. And that way, you are going to be able to rationalize a little bit about how to think about the performance of a join query and how to think about tuning for joins and that kind of stuff based on what's going to work under the hood. So the first use case here that I want to talk about is a SQL join operator on Druid lookups. So classic Druid lookups have been around for a while. They satisfied some of the same cases as joins, although they're not as flexible. One way they're not as flexible is that they're string-to-string key value mappings. So there's only one key and one value. Lookups are really in Druid treated as functions, or they were until now treated as functions. So a classic Druid lookup, let's say you wanted to take the destination airport ID and get the airport name instead of the airport ID. You would write this query down here. Select lookup of the destination airport using the air_port lookup, which is a key value mapping in this scenario we define, a key value mapping of airport ID to airport name. Count star from flights fact, group by one. So we're getting all the airport names along with how many flights are involved with that airport. And there's a couple interesting things about this, about the way this query is written. One is that we are doing some of the same use cases as you might do with the fact dimension join in traditional SQL. We don't actually write the join keyword. So this is classic Druid SQL, which didn't support joins. So we don't write the join keyword. We name the lookups. So this lookup is called air_port, and it's just provided as a string. And it's provided as a string input into this lookup function. And so really the way that we modeled lookups in the past versions of Druid was as these sort of magical things you loaded out of band. There's a whole separate system in Druid for loading lookups. You load them out of band, and the SQL layer doesn't really have deep understanding of what they are or what their schemas are. It just, you can refer to them by name as strings, pass them into this lookup function, which will then apply them. So the first use case we wanted to tackle with SQL on Druid is being able to do real SQL joins against these classic Druid lookups. And so the same idea here, the same query idea here, but with the join keyword. So now we have flights fact, inner join, airport join on flights fact.dest airport ID equals airport join.code. And so you have, there's a couple interesting things here. This query actually is going to run under the hood. It's going to run using the classic Druid lookup, but the SQL layer now understands about it, now knows how it works. This actually should say inner join. It should say lookup.air_port. I should have edited this, but that would match what was on the previous slide. Air_port lookup. This should be inner join lookup.air_port. And the lookup dot is what you would use in Druid SQL to signify that you want to query a lookup. So this enables using the classic Druid lookup feature, using the join keyword in SQL, which is nice for a variety of reasons. One is kind of cosmetic. One reason is that it looks more like the SQL you're used to. It helps analysts understand what's going on. It's more familiar to people. This kind of query can be generated automatically by business intelligence application, whereas they cannot automatically generate lookup queries. So it aids in integration with those applications. It aids in getting people to use Druid that aren't familiar with its language. So that's all good stuff. That's all relatively cosmetic stuff. There is also some stuff happening here under the hood that's less cosmetic. One of those things is that the SQL layer actually knows what the lookups now. So it can validate them at query time. It can validate them at planning time. Whereas with the lookup function, it didn't know what they were. It just knew they were strings. If you passed in one that was invalid or had the wrong schema, it wouldn't be able to validate that, but now it can. So it improves the strength of the validator of the SQL queries. Another potentially more interesting thing that's happening under the hood is that the join operator is actually, it's actually a real join operator. So the lookup function in Druid was just modeled as a regular function. It was almost like, it's not a UDF because it's built in Druid, but it's just a regular query function. Neither the SQL layer nor the native query layer treated it any differently from, say, substring, for example. The join operator actually is in Imply 3.3 and Druid 018 a real honest to goodness join operator. So that means a bunch of things. It means you can do not just inner joins, you can also do left joins. You can do cross joins. You can do all these different kinds of joins. It's able to do what a real join operator does, which is depending on how many rows you have on each side of the join table with a particular, on each side of the condition with a particular value for the condition expressions. You may get one row out the other end, you may get multiple rows, you may get 0 rows. So you can use these joins as filters the way that you could use an inner join as filter. You can use them to even blow up the side of the data set and return multiple rows for any one input row, just like you would expect from a join operator. So it really has been, even though in this particular use case I'm calling out SQL join operator on Druid lookups, even though the classic Druid lookups are defined and transferred out to the Druid servers the same way they've always been, the way they're processed has radically changed. When you write the lookup function, like on this slide, when you write this lookup function, it's just applying as a regular plain old function. And when you write the join keyword, it's not just syntactic sugar, it's actually running through a completely new query engine. So, okay, how does that new query engine work? Let's talk about that for a little bit. So here's an example here. Here's an example of doing a fact table to look up join execution. The fact table is the traditional Druid data source, and the thing we're joining against is lookup. So this is that query from the previous slide. Okay, here the query is actually written correctly. Flights fact join lookup dot airport underscore join. And lookup dot is how the SQL layer knows that it's a lookup table. So we're gonna get the description. We're gonna total the number of flights. and we're just going to return the results of this relatively simple query. So let's break down what's happening here. Just like in every Druid query, the broker is the service that first gets the query. And the Druid historicals are the services that have all the historical data and process the row by row aspects of the query. So the broker is what's responsible for parsing SQL and translating that to a native query. Excuse me, that hasn't changed. And it's also responsible for merging results, and that hasn't changed either. So what the broker is going to do is it's going to parse the SQL. It's going to fan it out as native queries of historicals. It's going to identify that these two historicals have segments related to the flights table, which is a regular Druid table. And just like lookups always have been, they are broadcast to every server. So every historical has a copy of this lookup table, airport _join. The join condition is going to be evaluated on the historicals. So each of those historicals then are going to, essentially for every row, they're going to get the destination airport ID from the flights fact table. They're going to look that up in the lookup table, which is going to have it's going to have a hash table based on the key. So it's looked it up in the lookup hash table, get the value, or see if there is a value. If there is a value, then that row is going to be emitted. And if there is no value and it's an inner join, the row will be not emitted, just as you would expect from inner join. And if there's no value and it's a left join, you'll get a null. Just like classic Druid lookups, the lookups live on the heap. So you can see here this sort of hybrid solution that we have in Imply 3.3 and Druid 0.18, where you have the classic way of distributing and modeling lookups as string, key, and value that hasn't changed. But you have this new way of executing them that is radically different at both the SQL layer and even the row by row layer, because the row by row processing is different. More about the internals. You have what you should expect as far as modeling your data. Fact table, okay to have billions of rows, even trillions of rows. This is the classic Druid scalability. We're very careful that any feature that we introduce is always needs to be scalable to those levels. And the lookup table, just like classic lookups, this part hasn't changed. Should be no more than thousands to potentially millions of rows on the right-hand side. Algorithmically, what's going to happen is that we're going to build a hash table for, this shouldn't say for every row and left and right-hand side. This should say for every right-hand side table. So for every right-hand side table, we're going to build a hash table. Then we're going to loop through the left-hand side to find matching records on the right-hand side using the hash table. So we're going to scan the left-hand side. We're going to scan the fact table. Every row of the fact table, we are going to get that key out, look up in the lookup table to see if the join condition has matched or not. This is why it's okay for the fact table to be as big as you want it to be, because we're just going to scan through it one time. We don't have to buffer anything in memory. It's a purely scan-based constant time, sorry, not constant time, but constant space process. And this is also why the lookup table is restricted in size. It's restricted in size because we have to build a hash table for it, and the hash table is going to be stored in memory. So this is what if you're a database person, you would call a broadcast hash join. So that is the kind of join that we've implemented in this version of Druid. Okay. Now I want to talk a little bit about on the next slide, getting a little bit about future work. So let's just pull it up and talk over it. So I mentioned that what you have in Druid 0.18 Imply 3.3 is actually a fusion of this totally new SQL syntax and totally new join operator that's happening under the hood, changing the way queries are executed, paired with really the classic lookup system for distributing and broadcasting this key value lookup data. It doesn't actually completely solve everybody's problems, because it still only supports for these broadcast tables string keys and string values in Druid 0.18. So what we want is the ability to move beyond lookups. This is work that's in progress. It's not actually in Druid 0.18. There's actually a preview of this in Imply 3.3 that is off by default. It's not ready for production yet, but it is available as a preview. So feel free to contact us afterwards if you're interested in trying it out. It'll be something that's available in a battle-tested production grade quality in future releases. So let me talk about this. This is replacing lookups and getting lookups out of the picture using something that I would call a join table. So the idea is instead of joining against a lookup, you join against a thing called a join table that whereas a lookup in Druid, the classic lookup has one key that must be a string and one value that must also be a string. Join tables could have any number of keys, any number of values. So they're really like regular tables, and also any types, not just strings. So strings, numbers, timestamps, any number of keys, much more flexible. Really able to store the same data types you would store in a normal Druid table. So the idea here is that they're much closer to what you would expect from a normal Druid table than what you would expect from a classic lookup. And this is great because it expands flexibility, it expands what we're able to do, and it helps unify the schema model a little bit instead of having to worry about the fact that, well, standard Druid tables support all these data types, and then lookups only support one, and they can only have 2 columns. Now you have a situation where standard Druid tables and tables that you're broadcasting for joins are actually much more similar. So it's behaving a little bit more like a classic RDBMS while still retaining the very low query latency and scalability that you're accustomed to at Druid. Again, we're like everything we do in Druid, we're really careful about how we roll out features like this because we want to make sure that no matter what we do, it's able to be done in a scalable and sub-second way. Okay, so what happens here? What happens here is actually very similar to what happens with lookup join. So what we're using with this, the prototype that I said that we have available as a preview in 3.3 and the battle tested thing will be in the future, it's using the same join operator that's shipped in Druid 018 and Imply 3.3. So that join operator is the wave of the future, and it rips out the lookups and replaces them with these join tables. In the current working version of our code, the join tables still live in the Java heap, so they're still limited by the size of the Java heap, although we are evaluating options for moving them outside the heap, allowing them to be even bigger, potentially. Although the broadcast nature of them is something that we're going to stick to. We're going to stick to having them pre-broadcast every Druid server, as opposed to being broadcast during a query. And the reason for that, of course, is query latency. We want to have the join tables already available before you query them, just like you're accustomed to at Druid, which enables that sub-second latency. So anyway, exciting stuff coming from the future. Please reach out to us if you're interested in chatting about it even now. Okay, so that's it for joins. It will take questions at the end, like Elisa mentioned, but for now, I have a couple of slides about the other topic I wanted to talk about, which is query lanes. Okay, so query laning is dedicated resources for, dedicated resources for high priority queries, and avoids short and fast queries waiting for long running queries. So that is why, let me go to the previous slide. That is why the graphic we have is a graphic of a carpool lane. The idea is that with query lanes, you have regular lanes, and then you have high priority lanes. And the high priority lanes are like a carpool lane, dedicated space that is only available for your high priority traffic. Just like a carpool lane, high priority traffic can use the regular lanes as well, but they don't have to. They have a special one just for them, and reserving it for them enables them to get the best quality of service. So here, I want to talk a little bit about the problem today that query laning is meant to solve. So we have a concept in Druid today of query prioritization, but the query prioritization concept in Druid only affects CPU use on the Druid historical servers. So it ensures that they all get, that a high priority query gets priority for CPU time slices on historical servers. But what it doesn't, what query prioritization previously to Druid 018, did not help with is resources that are higher level than that. So, and specifically resources that limit the number of concurrent queries. So the one I want to talk about now, the one that correlating is designed to help with, is Druid server threads. So the problem that we're solving is that each Druid query requires one thread on the broker to handle. And this is something that's been the case in Druid since the beginning and still remains the case. Every Druid query requires one broker thread. There's a limited number of threads. It's given by this Druid server HTTP num threads parameter. It's usually on the order of a few dozen per broker. So the idea being that per broker, 40, 50, some odd queries are able to run concurrently. This thread is used. It's tied up handling that one query from the moment that the user is connected to the broker until results are returned to the client. And the issue that can happen is on a large cluster with heterogeneous workloads, where you have some workloads that are interactive and some workloads that are reporting based. These long running queries can potentially use up all the connections. Let's say you have one broker. That one broker has 40 threads. If you have 40 queries running that are all going to take, let's say they're just doing really long running reports, big reports. They're not going to be sub-second. They'll take maybe a minute each. That would tie up all 40 for a minute if you have 40 running at the same time. And that means that regular queries, interactive queries cannot run. They'll have to queue up and wait, and then they may time out. So how do we approach this, which we will discuss as soon as the slides flip. Oh, there we go. Okay, so how do we approach this? We approach this with reserving some capacity for high priority queries. So if you look at this diagram shows the query scheduling system that was added in Druid 018. So it used to be that Druid server HTTP num threads, the outer box here on the scheduling diagram, was completely Wild West. Any query could run on it. It might not even be a query. Because the broker server threads do things other than queries. They also respond to health checks. So another issue is that if a broker was full up on queries, it would actually stop responding to health checks as well. They respond to health checks, they respond to metadata requests, they do various things that are not just queries. So one level inside, nested within server num threads, is the query scheduler num threads now. This is a new configuration. And this new configuration is the total number of queries that can be served. Its purpose is you generally want to set it to 1 or 2 lower than the server HTTP threads to ensure that there's stuff left over for health checks. And then another new parameter, Druid query scheduler max low %, is the max number of query threads that can run in the low priority lane. That is the most. So that's the most that low priority queries can use. And whatever is actually, I think that this diagram might need to be reworked a little bit because the reserve capacity is really what's not in that max low %. And the stuff that's not in the max low % is reserved for high priority queries. I guess if you think about max low % as being, let's say it's 20%, if you think about 20% of that being filled in, then the reserve capacity is the high priority capacity. Let me talk a bit about what happens to queries based on whether they're high or low. So if a query comes in and it's high priority, it can actually run anywhere. It can run anywhere, and that's great for that query. Good job, that query. If it comes in and it's low priority, it can only run in the low priority lane. And if the low priority lane is full, then I believe what happens today is that query will get rejected and the client's expected to try it again later. You'll get a special HTTP status code. I don't recall what it is, but it's in the documentation. You'll get a special HTTP status code that says, that indicates that it was rejected due to not having spare capacity to run your query, and you should try again in a little bit. And let's see. So let's talk about how we can decide what's high and low high and low priority? That's the big question. How do you actually decide which queries are the ones that get to use this special fast lane? Which queries have to slum it with the schlubs? So there's one more new config called the laning strategy. The default laning strategy is none. So by default, this feature is disabled, like a lot of new features. We may enable it by default in the future when its performance has been better characterized and its behavior has been better characterized, but we usually start things like this off as opt-in. So it's opt-in. There's two others implementations that we shipped with. One is high-low based on priority. So the idea here is that the user sets a priority, caller sets a priority. Anything above 0 is high, anything 0 or less is low. 0 is default, so by default it's low, but if you set it a little bit higher, it's high. And the third is manual, which is that the user will, the caller, the person who makes the query, will specify the lane it's going to go in as part of the query context. So rather than being based on the priority, they just explicitly say whether which lane is going to go in. That can also make sense. The idea about these two options is the high-low one is designed to integrate well with folks that are already using Druid query priorities. And the manual one is designed mostly for fancy special setups where you have some special logic that's going to be deciding what lane to put things in, and you've configured lanes a certain way. So the goal of this feature is to make it so these interactive queries in Druid are always going to be high performance, even if there's a lot of non-interactive queries happening on the same cluster. In a world of fixed resources, in a world where you don't have an infinite sized cluster, you have to do that by deciding who's going to get those limited resources, and we're going to ensure that there's always resources available for interactive queries. Okay, so those are the two things I wanted to talk about. I want to talk about joins, and I want to talk about how in this release we built and shipped joins on classic Druid lookups using a completely new syntax, completely new join operator under the hood at runtime. And I want to talk about how we've shipped in the Imply version, a preview of a next generation that will replace lookup tables and intend to make that battle ready and production hardened for future upcoming releases. And then I want to talk about query laning, which is a feature that is designed to keep interactive queries always performing well and maintain that low latency sub-second scalable goodness that you're accustomed to with Druid, even in the face of very varied workloads running on the same cluster. Okay, so last thing I want to say is we started doing weekly live demos, and check out this link that I'm sure you'll also get by email after this if you're interested in demos of some of these and other features. Okay, so that being said, that was all the material I had. It looks like we have a few questions in the Q&A, and I will look at those, and then maybe I'll hand it over to Elisa if in case. Elisa, do you have any final things you'd like to say after the Q&A?
No, do you want to do the Q&A?
Yeah, I'll do it.
Okay, great. Yes.
Okay.
You at the Imply demo, we have them every Friday and they're in local time. This week we're doing London time and Pacific time, and then next week we're adding in the Asia Pacific area as well. So if you want to get familiar with some of the features, benefits of Imply, I would invite you to register for one of these. Okay, go ahead, Gian.
Okay, so I think we have another 10 minutes or so. So we'll answer as many questions as we can in that time. So feel free to ask whatever you would like to ask. Okay, so the first question that came up in the Q&A is, are we able to join on multiple tables too? Yes, we can join on multiple tables too. The join operator that we built and shipped in this version is actually a multi-join operator. So it's able to take, the only restriction is you can only have one classic Druid table. You can only have one big distributed regular Druid table. So we'll refer to that as the fact table or the main table. So you have one main table that's a big distributed Druid data source, and then you can have as many other lookup tables or in the future join tables as you want. One thing that I didn't mention is that this release also adds the ability to join on subqueries. That's actually an important feature, but I didn't include slides on it due to time constraints. But you'll be able to join on subqueries as well, and that's useful for things like filtering on subqueries. And you can have as many of those as you want in a single query as well. So you can actually get pretty complex with the SQLs you can write in this version. Okay, what was the next one? Joins without lookups. Any of it estimate when it will be available in Druid, so that well, in a sense today, because you can not just join on lookups, you can also join on subqueries in Druid 018, and you can join on what we call inline data sources in Druid 018. Inline data sources are just what they sound like. In the query, you specify data. But if you meant joins not in the subqueries or inline data sources, but joins onto those join tables, then I would say next 1 or 2 major releases. It's something that's we're actively working on right now. Question about laning. Are the dedicated resources in the idle state until a high priority query shows up? Yes, they are. They are dedicated in that sense, but it's not as bad as it sounds, because the only resources that are really dedicated like this are those threads in that thread pool for concurrent queries. So what this really means is that we're limiting how many concurrent low priority queries can run at once. So let's say if you have, like a typical broker would have, let's say 40 or 50 concurrent queries able to be run at once. You might, let's say it's 50. You might limit it such that only 40 or 30 of those, can be low priority. So it's still quite a lot of low priority queries, and it's only limiting that thread pool resource on the broker, which is only 1 per query anyway. Low priority queries can still access the full resources of the historicals, which means that in terms of how fast they're going to run, a single query will still run just as fast as it would without query laning. It does not lower the speed or affect the speed of a single query. It just affects how many concurrent low priority queries can run. So we made sure to design it that way because we did not want to design a system that would lead to queries actually running slower. Good question though. Let's see, a question about SQL libraries. So do I have or suggest any SQL client libraries? Can you use a Spring Data or any such packages? I am not too familiar with Spring Data, but we do have a JDBC driver that's available on the Druid website. Go to Druid SQL docs, search on that page for JDBC. You'll see a link to a project called Vatica. It's an Apache project, Apache Vatica, or maybe it's a sub-project of Apache Calcite. Either way, it is a JDBC driver you can use to make Druid queries. So that's the one I would suggest if you're using Java. And if you are not using Java, then we have a web service that is actually very easy to use. You send the query wrapped in a JSON and then you get the response back as either JSON or CSV. You can actually tell it what format you want. So if you're not using Java, I would recommend that web service. By the way, the final comment, the JDBC driver is the recommended way for integrating with business intelligence applications. Unrelated to 018, but can you comment on how you would recommend handling nulls versus zeros in Druid? Interesting question. So I think we actually added docs on the SQL compliant null handling in 018. It was either in 17 or 18, so it was somewhat recent. But we have a new, relatively new mode in Druid for SQL compliant null handling that differentiates between zeros and nulls in a way that classic Druid did not do. There is a performance overhead to this of course, because you imagine having to deal with nulls is a little bit more performance overheady than not dealing with nulls. But if it's important to you for the behavior that you want, the performance overhead is not that big. It's not, you know, it's measurable, but it's not huge. So I would suggest turning that on and playing with it. If the behavior you would like is for nulls and zeros to be treated differently. Question, what are the constraints of the joint operation performance? Any specific rules we should remember? So there is an overhead. We're working to get it as low as we can. So join queries are as close as possible to queries as if there was no join at all. It's of course not going to be possible to get it all the way down to no overhead, but we're trying to get it as low as we can. We've actually already made strides since shipping Druid 018. So in master, it's actually already significantly faster. So 19 will have even more improvements here. But I would say that in 18, depending on the query you're doing, you should expect overhead of somewhere between, I would say 50% to 4x overhead over a native query or over a flat query, depending on what it is you're doing exactly. So I would try it out for yourself to see what kind of performance you get. And then keep in mind that that's already better in master, and we'll be getting better continuously until we get it down low enough that we're happy. And because we're Druid people, we're not going to be happy until it's pretty low. Can we configure query laning on the fly? As in, if the number of high priority queries keeps increasing and the reserved capacity is not enough, can we somehow set the context to raise the capacity temporarily? The laning configuration currently is in the runtime properties of the server, which means you do have to restart the server. But you can change priorities of queries on the fly if your strategy that you configured allows prioritization based on query context. So if you think you might want to do a lot of on-the-fly changes like that, then I would use one of the strategies that allows you to modify what lane things go in, what priority they have at query time. A question about joins. What are the main challenges in introducing joins between two Druid data sources? If you mean between the two big ones, two regular Druid data sources that can scale out to billions of rows, the biggest challenge is that the join operator we implemented today is a broadcast join, which relies on all the tables but one being broadcast to every server. And the one table will not be broadcast, and that's going to be that base table, the big one. You actually, in Druid 18, can join two Druid data sources. You can write that query and it'll run. But what's going to happen is that the planner will take one of them and broadcast it to every server, and the other one will not be broadcast. And so if the one that it broadcasts is large, if it's more than a relatively manageable amount of rows, then you'll get an error at some point in the query that I think it says subquery maximum number of rows exceeded, something like that. So the biggest challenge is implementing a non-broadcast join operator. You can't broadcast a giant table to every server, so you have to do something like shuffling based on a join key. So that would be the main challenge, is implementing a shuffle join or some other kind of join. How to ensure no data loss during transmission, as it doesn't have ACID property of database. I am not sure exactly what you mean by this. Druid's interesting. It's interesting in its design. It's interesting in that a lot of the stuff in ACID and how people think about ACID revolves around, well, a couple of things. One is, are your writes durable? And the other one is, do you have consistency around reads and writes, such that I can write something and then I can read it back, or I can write something and then if someone else reads it, then the history is linearizable there in some way. because Druid's ingestion and reading systems are separated, I would say that a lot of those ways of thinking don't really apply, because you're actually not supposed, it's not a transactional database. You're not supposed to be able to write something to it and then read that thing back immediately. That's just not how it's meant to work. So those parts of it are not supposed to be ACID, and I think for the kinds of things people use Druid for, that's fine. And it's what allows it to be as scalable as it is. But we do care a lot about the other thing, which is data durability and not losing your rights. So when you're reading from Kafka, when you're reading from S3, when you're reading from HDFS, we always make sure that we do an atomic read from those systems, and so you get all or nothing behavior. And that all or nothing behavior is good because it means that you don't have to duplicate or drop data. And it also means that we make sure it's durable once ingested. So once it is written to deep storage and metadata store in Druid, it's not going to go anywhere. It's not going to magically get rolled back. So we do have very strong durability and atomicity processes on writes. We don't really connect that to the read side. We keep them quite separate for architectural scalability reasons. And that seems to work for most people. You mentioned we are hiring. Do you hire in Europe? I believe so. Check our careers page, Imply.io/careers. Does it support ANSI SQL? A subset of ANSI SQL, not all of ANSI, but the stuff that we do support is ANSI. It's a subset. Where can we get the latest JDBC driver? Check out the Druid SQL docs. Search for Avatica. Why is there a limit of distinct count to 1 when querying with approximate count distinct set to false? Aha, that is a good question. That is a very inside baseball question. Karthik, thank you. The reason is actually also very related. So thank you for this, teeing this up for me. It's because under the hood, the way that multiple distinct counts are going to get done, if you set them all to exact, is it's going to get planned into native queries. It's going to get planned into a native query that actually does each of the distinct counts separately and then joins them together, joins the results together. So it actually depends on being able to join subqueries under the hood. It's one of those places that joins come up in surprising ways. It's actually still not possible to do this in 018 because we didn't implement quite enough stuff to make it possible, but it will be possible in a relatively soon upcoming future release to have this query planned properly. Great question. Okay, we're just about out of time, so I will pick one more randomly. I wish I had a four-sided die on me. Well, I'll just take the first one. Okay, first, will the future iteration lookups have a history? Meaning, will it be possible to use past data? I assume you mean being able to have a snapshot of the lookup table itself. Not something that we have been planning, but it's something that I would say could make sense in the new framework. So I wouldn't rule it out. Okay, fine, I'll do one more because I like the next one. Any updates, deletes in the works? Great question. We just recently kicked off a design discussion about how we can do updates and deletes in Druid in the future. It's not something that's being actively worked on, but it is something that is being thought about and talked about. And I think that Druid of the not too distant future will have some kind of support there. If you're interested in the community discussion, it is happening on the Druid developer list, which if you go to the druid.apache.org page, click on community, you can see links to the developer mailing list and developer pages. And there's some discussion happening there about this topic that will eventually make it into a release. Okay, I think that's all the time we have. So at this point, I'll ask Elisa, any final things you want to say, or are we set?
Well, I think we're set, everyone. I want, Gian, thank you for a great presentation today. There was a lot of interaction, a lot of great questions. And we hope to see you in a future webinar, which we will be updating our webinar calendar in the next couple days. And I'll send out an email to you guys to let you know what the next topic is. Also hope to see you on the live webinar if you would like to see more about Imply. So again, thank you for attending. And Jian, thank you for a great show today.
Thank you too.